Good morning everyone, welcome back to the stream. Today we're gonna try to continue with the Vulkan tutorial and put some texture on the screen. So last time we left out loading the image using the STV library. So you can see here that we implemented some bindings for STV instead of using a crate. So we were able to load this JPEG texture, and also we created a staging buffer and copy the data into it. I have here this to do to clean up the resources, but we're gonna do it later on. So if we run the program, we still have the previous behavior where we have a rotating rectangle, and when I quit we get some validation errors because we are not cleaning neither the buffer nor the device, the staging buffer memory. So yeah, that's what this to do is all about. So before I continue, I want to move out all of this code into a separate function because that's what they are doing on the tutorial. So I'm gonna grab all of this and move to the bottom down here, and maybe somewhere in here. I'm gonna add a function fn create texture image, maybe something like that, and paste the code in here. This is probably gonna be unsafe. I need to wrap this. We're gonna need at least the Vulkan device, so we need to pass it in. And we need anything else. Also the physical device is required to create the buffer. Pass it in as well. So I think it looks good now. That's the function that we are just creating. Here we create the buffer and copy the image data or the pixels into it. And next up, we're gonna have to create the actual texture image. So before I do that, let's not forget to call this function in here. So create texture image, which takes the device and the physical device. We're probably gonna return something. But for now, I think it's fine like this. So I was saying, after mapping the memory and copying all of them, we need to create the actual image. So let mute texture image. It's gonna be a null pointer initially, and then we can probably create the image. So we're gonna need the create information structure as usual, and fill in some of the structure parameters, the layout, the usage, sharing mode. But the function we're interested in is this bk create image, which I can put in here, and I think it can fail, so let's wrap it in the check macro. And this takes the device, this image info, pk image create info, null pointer for the allocation callbacks, and the output parameter texture image, like so. And here we need to fill all the fields of this creation structure, which is going to need s-type, info. Probably we're going to need pnext. So we can already take a look at this. I want to see the actual definition for this function in the Vulkan header, so we can search for it, create image. Here it is, and we just need to add it to our list of bindings. Here we have all the Vulkan functions that we are using so far, and we need to add one more. Create image view, maybe up here. Create image, text the device, the create info. The allocator. And returns a pointer to an image. Like so. And we can also add already the counterpart, the bk destroy image, to clean this up. We're going to need to do that at the end of our program. bk destroy image plus image and allocator. Next up, we need to create the structure, because so far we don't have it defined. So copy that, navigate to maybe image view create info. Yeah, we can add it before this one. Contains the structure type for sure, and we can look what else does it take. All of this. So also a pointer to pnext, some flags. The image type, whether it is 2D, 3D, a cube, the format, extend, let's extend 3D, weird, new levels, array layers, samples, this should be actually a sample called work bits, but This one is a set of constants, and this one is the actual enumeration, I think. We'll see if we need to change it. So samples. How do we want the tiling to be for this texture? To such. The cube family. Which we can actually provide more than one. So we need to provide the count and then an array of the indices. And finally, the initial layout for the image. And now let's see which ones of these types do we have to find and which ones we don't. Let's add a marker here and go to our list of flags and add this one. Next, we need to define this image type and the image styling. So that's the only two things we're missing. Image type is this enumeration. So grab it. Actually, here, I think we can put it down at the very bottom where all the enumerations are. Copy this, paste this, sorry. Make it public, get rid of this, and then export all the variants from this enumeration. And if I recall correctly, we also need the image styling. Is it an enumeration as well? Yeah, it's up here. Copy this one as well and do exactly the same. Check I'm not missing anything, and check that we can compile this. Okay, we get some errors, but they are because we are missing all the fields basically on this structure. So I should be able to grab this. Can I just grab basically all of this, go to main, paste it in here, and then we don't need the type or the flags. Oh, sorry, the flags, we don't need them. Then get rid of this, properly align this. I think I didn't grab the proper ones. Yeah, I grabbed the ones from image view. Shame on me. So back to OK. We want these ones. And again, get rid of the public. For the flags, I think we want 0. And now let's see how do they fill all of this. The image type is gonna be image type 2D. The format is gonna be format RGB8, RGBA with 8 bits and sRGB. So paste this in. Then the extent is just the text width, text height, and depth of 1. So we can fill this in directly here. Width is gonna be, what did we name these things? Width, height. But maybe we'll need to cast. So depth just 1. Mid levels, I guess we're gonna have 1, and the same for layers. Yep. And the tiling is gonna be optimal. For the samples, I guess we just gonna have 1 sample. Yeah, sample count 1 bit. Then we need the usage. It's gonna be transfer destination and usage sample bit, or pin together, since this is a bit flag field. And then the family count. What do we need for the families? Do we need to set them at all? I don't see we are using them anywhere in here. So I think we can just set them to 0 and 0. And the last one is the image layout. Sorry, the initial layout. We're gonna set this to undefined, meaning then that we don't care about the initial layout. So now this should be compiling, and it is. So that's all it takes to create an image. Just fill this big create information struct with the proper information. Now let me just try to understand what each field means. The image type tells Vulkan what kind of coordinate system the pixels in the image are going to be addressed. It's possible to create 1D, 2D, and 3D images. 1D can be used to store array data like a gradient. 2-dimensional are used for textures, and 3-dimensionals can be used to store voxel volumes, for example. The extent specifies the dimensions of the image. That's why depth must be 1 instead of 0. Our texture will not be an array, and we won't be using MIG mapping for now. The format should be the same as the pixels, as the pixels in the buffer. Otherwise, the copy operation will fail. Tiling can be linear or optimal. So tiling linear means that the pixels are laid out in row measure order, like our pixels. Unlike the layout of an image, the tiling mode cannot be changed at a later time. The initial layout can be undefined or pre-initialized. Okay. And these are just some slightly advanced use cases, I think, so we're just going for the basic case. Then the sharing mode can only be used by one family, so share exclusive. Samples, it's gonna be one sample, we don't use any kind of multi-sampling. There are some optional flags for images that are related to sparse images. Sparse images are images where only certain regions are actually backed by memory. If you were using a 3D texture for a voxel terrain, for example, then you could use this to avoid allocating memory to store large volumes of air values. We won't be using this here, so we don't need it. The image is created using VK create image. We already have that. It is possible that the format we specified is not supported. You should have a list of acceptable alternatives and go with the best one that is supported. However, support for this particular format is so widespread that we'll skip this step. Using different formats could also require annoying conversions. We'll get back to this in the depth buffer chapter where we'll implement such a system. Alright, so after we've created the image, we need to get the memory requirements for it. So down here, let mute memory requirements. It's gonna be this structure, BK memory requirements. And maybe we can initialize it to default. And then we call this get image memory requirements, passing in the device, the image, and the memory requirements. And we need to define this one as well. Get image memory requirements. I think we had a similar one for BK get buffer memory requirements. Yeah. So we can add it in here. BK get image memory requirements. Specify all the parameters that we need. I think we already have the memory requirements structure defined elsewhere. So that's why it doesn't complain about this. Now going back to main, this should succeed. And with that out of the way, we can allocate memory for the texture. Which is very similar to what we were doing for the buffers, for the vertex buffer, for the index buffer, for the uniform. So we need the device, we need some memory allocation info. Then for the allocator, as always, we can use null. And we get back some texture image memory. Texture image memory. find it up here. And if I remember correctly, this one can fail. So make sure to add a check for it. And now we need to fill in the structure. Memory allocate info. We also need pnext. The allocation size, which here they... Okay, we just get it from the memory requirements. So memory requirements dot size, was it? Memory size. Size, right. And finally, the memory type index. We created a function for that. Get memory type. I don't remember what I called this. Find memory type. Find memory type. Takes the physical device. The type filter. The type filter can be the memory requirements, memory type bits. And the properties is a flag field of the properties that we want. In this case, just a memory device local, like this. Cannot find. Okay, I mistyped here. It should be allocate info, not allocation info. Types differ in mutability. That's because we need to pass this by mute reference. Now this should compile. Okay, we get a bunch of warnings, but no errors, so that's fine. Next, we need to bind this memory that we allocated to the image that we also created. So we use this bind image memory function, and it takes the device, texture image, and texture image memory. Anything else? And 0 for the offset, I think, should be. Yeah, it's the memory offset. So get memory image requirements and decay bind image memory. This function might fail, so we should add a check for it. Basically, I want to know the first point where the program starts to misbehave. Next, what do we need to do? Allocating memory for an image works exactly the same way as for a buffer. Yeah, we saw that. And for binding, we need to use VK bind image memory instead of bind buffer memory. This function is already getting quite large, and there will be a need to create more images in later chapters, so we should abstract image creation into a create image function. I'm not gonna do that yet, because just take a look at the amount of parameters that they are passing in here. My god. Okay. So we create the image, passing in all these parameters. And next, the function we're going to write now involves recording and executing a command buffer again, so now's a good time to move that logic into a helper function or two. So this one takes the command pull the device. Yeah, I'm gonna create this too. I'm gonna create this too. Begin single time commands. Can put it down here. Begin single time commands. Probably takes the device, the pull, but what kind of pull was it? Command pull. And does it take anything else? The command buffer is allocated in here, so I think that's it. But we need to return the command buffer that we allocated, right? This is gonna be super unsafe, so make sure to mark it as so. And we allocate using the allocate command buffers, takes in the device. This VK command buffer allocate info, and gives back the command buffer, which we need to declare in first. And I don't remember this one, if it can fail or not. We still have to mark this that it's not done yet. Yeah, it can fail, and if you go to the command buffer, allocate info, we're gonna need all of this. So add a check in here. And now it's time to fill in the structure. The structure type is gonna be BK structure type command buffer allocate info. Phoenix, it's gonna be just null pointer. The command pool. The level I think is gonna be BK command buffer level primary. We don't deal with secondary buffers for now, and I think we just want one command buffer. Am I right? Or we want, yeah, we just need one single buffer. we get it back, and immediately after that we can begin recording into it. So add this second function call, takes the command buffer and the begin info and this one. Takes in just some flags and the structure type, of course. Next, nothing. And for the flags, and also inheritance info. For the flags, we just need one time submit. The inheritance, we can just ignore this one. And now we just return the command buffer. This one should be the command pool. I think now we are good. We can add the other function. I think they called it end single time commands. End single time commands. It's gonna take also the device and the command buffer. And this one doesn't need to return anything. So pk and command buffer, and we just pass the command buffer. This one, not sure if it can fail. It can fail, yeah. Do we need anything else in here? Oh, we stop recording commands and we submit also to the graphics queue. So after all, we're gonna need the device, the graphics queue, and the command pool to free after us. Yeah. So device, graphics queue, command pool, and I think that should be everything we need. Yep. So we need to submit into the queue after recording. Takes the graphics queue. We just want to submit one submit info. Command pool, Python type. Submit info. Where are you? In here. submit info, maybe? Submit info, yeah. Next, we don't need anything. I'm not sure we're gonna need semaphores in this case. No, we just gonna need the command buffer, so all of this can be basically, well, the wait count is gonna be 0 and the pointer can be pointer null, pointer null, one command buffer, zero signal semaphores, zero or null here as well. Queue submit also takes a third parameter. That should be all it takes. Yep. Then we need to wait queue, wait idle for the queue to complete this operation. Which can also fail. And finally, we can free the command buffer. Yeah, free command buffers. Next device, command pool, count, and the command buffer. This one just returns void, so no need to check for the result. We're still good. So the code for this function is based on the existing code in copy buffer. You can now simplify that function to... Okay, so now we can in copy buffer, if we do have this function, yeah, in copy buffer we can now replace all of this, allocate and begin with, we can basically do let command buffer is equal to begin single time commands, passing the device and command pool, and we can get rid of all of these. Then we do the copy command, and after that we do end single time commands, takes the device, graphics queue, command pool, and the command buffer, and we can get rid of all of this. Let's make sure this still runs. We should probably get some validation errors, but we should still be seeing the rectangle. We are getting validations on the creation of image. Something about the initial layout. Unhandled. So what is this image layout undefined defined as? Oops. BK image layout undefined. Is just 0. On BK create image 110. Is maybe the usage I think I might have made a mistake in here copying the bindings, so I want to see if maybe one of these is 110. Fine, we are gonna image styling. But this one is not 100 and is not 101 for sure. This one should not give us any problem. But maybe the usage. This one is 6. And we're not getting any problem now. We only get the problem when destroying. Maybe did I not save? I think I didn't save. Huh. Interesting. Let me go to the BK image create info. Did I not add the wrapper C? Yes, it's here. Let me compare this carefully. S-type, pnext, flags, image type, format, extend, MIP levels, array layers, samples. Maybe this one is the problem. Tiling, usage. Oh, I forgot. Yeah, you see, I made this silly mistake. After usage, we are missing the sharing mode. Okay, sharing mode. Probably you saw that while I was doing it. Extend, sample firing, usage, sharing mode. Could be what? Sharing mode. Sharing mode exclusive. So now we just get the validations error when we quit, because we are not destroying everything that we should be destroying, but that's fine. Where were we? We were on the copy buffer, which we replaced to use the begin and end single time commands. Let's go back there. So we're gonna need this transition image layout function. Transition image layout. Not sure what it's gonna take, probably the device. And probably the image. Yes, takes the image, the format, the old layout, and the new layout. So let's add this in. I really forgot the image, the format, old layout. This is type BK image layout, and the new layout. Probably gonna be unsafe. We begin a command buffer. That's why we created these methods, right? Device, command pool. We're also gonna need the command pool. And at the end, and single time commands, device, graphics queue, command pool, and command buffer. So on the signature we need device, graphics queue, and command pool. And now, which commands shall we use? Command pipeline barrier. We don't have this one yet in our binding, so let's grab it. Pipeline barrier. Fix the source and destination pipeline stage. Any dependency flags. The amount of memory barriers. The actual memory barriers array. And we can also have buffer memory barriers. And also image memory barrier. Hopefully I did type this correctly. It looks like I didn't, or maybe it's because we are missing these types: memory barrier, buffer memory barrier, and image memory barrier. Start with the BK memory barrier. Access. Destination. We also need the image memory barrier. Start the image memory barrier. And before that one, we also needed public struct bk buffer memory barrier. How's it? Where is it? Okay, buffer memory barrier. Yeah, this one. Takes exactly the same as this one, plus some additional stuff. Access flags, source, destination, source queue family index, and destination, a buffer, an offset, and a size. And for the image memory one, can grab all of these. Plus an additional old layout. And a new layout. And we also need source queue family and destination, the same as here. What else? We need an image now instead of a buffer. And finally, a sub-resource range. Okay, image sub-resource range. And do we have this one? Check if it compiles. I did not see the error very clear. So we get some warnings. Expected parameter, but found asterisk on 358. 358. Command buffer source dependency. Here we're missing the name. No problemo. It was called P image memory binders. Like this. Let's plug the name. Now we need to fill in all of these parameters. We need the command buffer. Source stage is going to be to do. Source stage. Okay, let's set 0, 0, 0, 0, null pointer, 0 and null pointer, and the last one is gonna be 1 and this image memory barrier. The source access mask is gonna be... They don't specify it. So I guess 0, 0, all layout is the parameter that was passed in, old layout and new layout. The source queue family both can be ignored. That's right, if they are only used if we wanted to transfer ownership from one queue to another, which we don't. The image was also passed in, and the sub-resource range. Okay, sub-resource. Takes all of this. So the aspect mask, color, base, mid level is either 1 or 0, 0, but we have one level, base layer 0 and layer count 1. Now we're just gonna have to deal with this. Okay, we don't have the queue family ignored. type was this? I think it was a U32. Yes, they are U32. We can add it here with our constants. Let's put it true, false, UUID size, new family, ignore, U32, and it's just all ones basically. So bitwise negation of 0. That should be all we need as far as this is concerned. And now we're gonna have to read and see if we need to set this to something. Barriers are primarily used for synchronization purposes, so you must specify which types of operations that involve the resource must happen before the barrier, and which operations that involve the resource must wait on the barrier. We need to do that despite already using queueWaitIdle to manually synchronize. The right values depend on the old and new layouts, so we'll get back to this one once we've figured out which transitions we're going to use. So I want to add comments for these things. So this one we're gonna need, this one as well, and also the source access mask and destination access mask. So these two also we're gonna have to set. All types of pipeline barriers are submitted using the same function. The first parameter after the command buffer specifies which pipeline stage the operation occurs that should happen before the barrier. The second specifies the pipeline stage in which operation will wait on the barrier. If you're gonna read from a uniform after the barrier, you would specify a usage of access uniform read. The third parameter is either 0 or dependency by region. Copying buffer to image. So we do this on yet another function. We can add it up here. We're gonna need all of this. Device, graphics queue, command prompt, at least at least we're gonna need this. And then probably a buffer image with some help. Buffer image with and height. And now the command we need is vk command copy buffer to image. So this is just a simple wrapper. The only thing we are missing here, I think, is this vk buffer image copy. Buffer image. One on the region, which is vk buffer image copy. Buffer offset, I expect to be 0. Buffer row length, it's gonna be 0. Buffer image height, it's also 0. Image sub resource. Ooh, I did this wrong. This is image resource layers, not image subresource range. Layers. And this one is defined up here. Speed mask. Aspect mask is color. Level. Did I type it correctly? Yeah. Base array layer is 0 and layer count 1. We also need the image offset. Which I expect can be all zeros. And the image extent. With a width of 5 and depth of 1. Width and height are passed in, and depth, is it 1? Yeah. Base array layer. Let's see. This compiles. Looks like it does. Preparing the texture image. So now we are ready to finish the create texture image, which we have up here. Create the image, we allocate memory, we bind memory for it. I think we can free also. In fact, I would expect that right after we copy the pixels to the staging buffer, we are ready to free them. So here, after binding, we conceptually need to transition. Takes the device, graphics queue, command pool. This should be texture image probably. Format. And we're gonna have to add a bunch of parameters here. Format, I don't know what should be. Should be this. Old layout is undefined, and the new layout is optimal for transfer destination. So we need the graphics queue and the command pool. So graphics queue and the command pool, like so. This function was not completely finished. I think we needed to deal with the transition barriers, yeah. But right after we transfer, we can copy buffer to image. Device, graphics view, command pool, staging buffer, texture image, width and height. The image was created with layout undefined, so that one should be the old one. And transitioning to texture image, remember we can do this because we don't care about its contents before performing the copy. To be able to start sampling from the texture image in the shader, we need one last transition to prepare it for shader access. We transfer from destination optimal to shader read-only optimal. So, transition. Well, it's gonna be easy to just copy this. Format is the same, and this is now the source, and the destination format or layout should be shader read only. Something along these lines. If you run your application with validation layers enabled, then you'll see that it complains about the access masks and pipeline stages in transition image layout being invalid. Is that so? Is that true? I'll run. Well, first of all, we don't even compile. So on line 407, we need the graphics queue, the command pool, and I think that's all. So, okay, we got some validation errors. Source stage mask must not be 0 unless synchronization 2 is enabled. Source stage mask must not be 0. Destination stage must not be 0. Yeah. So we need to specify this transition barrier masks. If you run your application, okay, there are 2 transitions we need to handle. From undefined to transfer destination, transfer writes that don't need to wait on anything, transfer destination to shader reading. Shader read should wait on transfer writes. Correct. So after we have not written the image with the data from the buffer, the shader should not be allowed to read. Makes sense. Specifically, the shader reads in the fragment shader because that's where we're going to use the texture. Okay. These rules are specified using the following access masks and pipeline stages. if old layout is undefined and the new is best optimal, then the source access mask is 0, but the destination access mask is transferred. Okay, so wherever we were doing this, it's only one place, right? So we can add this logic. If and we are not using the format, so why do we then? Maybe we need to choose the source. I don't know. So if all layout is all layout is equal to this, and new layout is equal to vk image layout transfer destination optimal, I think. Else, if all layout is new layout is equal to that, we do some other stuff. Otherwise, just panic. Invalid combination of old layout. Put it here. New layout. Put it here. We need to implement or derive debug for image layout for that to work, which is easy to do. And we also need to derive partial egg, so we can compare this. Right. Yeah. Now it works. So in the case where image layout undefined and well, where the old one is undefined and the new one is transfer destination, we want to specify the source access as 0. So we should get source access 0. We're going to return just a tuple with the for and source stage is top of pipe bit and destination stage is transfer bit. So this is going to be source access best access mask source page best page. Is it called that way? Yeah, source stage. In the other case, source access mask is transfer right. And the destination would be shader read. The source stage is transfer, and the destination stage is fragment read, fragment shader. Where do I have the BK? Do we have a flag for 0? Access none. Yeah, I'm gonna set it instead of 0. BK access none. That way it formats it, yeah, similarly. Now in here, we can use the real thing instead of zeros. Source, the first two is source stage and destination stage. Source stage. Test stage, and the source access mask can be filled in here. Source access mask, as well as the destination access mask. Is that all it takes? So let's see. Okay, so now we got rid of the validations. Now we just need to deal with the cleanup, because we have been creating lots of stuff and we're not cleaning it up. The image will be written in the same pipeline. Okay, let's just try to clean all of this. So the staging buffer can be cleaned up right after the texture has been created. So remember, we have here the create texture image. We transition, we create the image, we allocate memory, we transition the image, we copy from the buffer, from the staging buffer to the image, and then we transition back. And after that, we can destroy the staging buffer memory. Well, we can free the memory first, and then we can destroy the buffer. Staging buffer. So that should get us rid of the errors of not cleaning up the... So we had 1, 2, 3, 4 validation errors before. Now we should get down to 2. And that is indeed correct. What do we have left to clean up? We have the image and the memory associated with that image. So we are gonna return that from this function as a tuple. So bk image and bk device memory, which should correspond to the texture image and texture image match memory. Then whenever we call this create image texture image, we can save the texture image and texture image memory. We store those and we can clean them up right before, well, after destroying the swap chain. so all the way down. So here we are destroying the command pool, index and vertex. Here we can clean up this. No, destroy image in this case. And let's run it one more time. Close, and we got rid of all the validation errors. I'm concerned about this unused format. 1526 in transition image layout. So I will quickly peek at the source code for this tutorial and search for transition image layout function. Transition image layout. Do we use this format anywhere? It doesn't look like we do. Fuck. Transition image. We have the format here. We don't use it to begin commands. We don't use it in the barrier anywhere. Here we don't use it for choosing the access and destination maps or the stages. We don't use it for the pipeline barrier. And we don't use it, so yeah, I don't know why did they add it. I'm gonna add an underscore, so maybe they will use it in the next chapter, who knows. So let's commit all these changes. I have changes pending from last time. So for instance, yeah, because we started using STV image. So are we gonna do a monster commit? Yeah, I think we do. I'm gonna just commit separately the git ignore, compile, source lib, build rs, source stv image dot c, stv image dot h. Not gonna commit the images for now. Status. So we can commit this as add bindings for stv image, and the rest we can add everything in source and commit as what did we do exactly? Create image, so create image and copy pixel data into it. That sounds about right. Push this. I need to set up the SSH agent properly because every time it asks me for the password. I don't like that. So yeah, that was everything for today. You can check out the source for the project on my GitHub, which I will share the link now. It's in here. And so far we were not able to see the texture on the screen, but we still have a working program with just the rotating rectangle. So thank you all for watching, and I will see you next time. Probably I will stream again this evening. So I want to finish this and see the texture. But yeah, until then, have a nice day. See you.